Today we're going to see when to use proof by contradiction in flag style derivation. So on the left we have a snippet of a derivation. The rest of the derivation doesn't matter because it's quite long. And we're going to see an example of when we should use proof by contradiction. Now, when my class was taught this in uni, we were told to use proof by contradiction as a last result, so you might have been advised the same. Maybe that's because they want you to use the rest of the rules first, rather than just proving everything by contradiction. But also because you might use it wrong and then prove something that's actually not true. So they always tell you to use it as a last resort. And in this example, you'll see that we're forced to use proof by contradiction because there's no other way of going about it. Okay, so let's see what we have in our question. So we're trying to prove Q of y, and we have three assumptions, 1, 2, 3. Okay, we've forgotten to write the number line here, which you should never do that. Okay, so we have three assumptions, and right now we have no reason to use proof by contradiction because, well, first we work on this assumption, let's see what we can derive, and then when we're stuck, that's when we use it. Well, the only thing we can do here is use existential elimination on line 2 to get rid of this existential quantifier. And in this example, we're going to use the alternative derivation rules for existential quantifier, not the normal ones. And just to clarify what I'm talking about, so if we have an existential quantifier like this on the right, and the normal rules would be, so if we use I'm going to write the hint here. If we use the normal rules, this is just going to be normal E LM on, and then we don't need to write the line because this is just an example. And here what we will derive is actually a for all x, if P of x holds, then not Q of x holds. This should be not square brackets. And from this we will have to derive false. So the alternative one would be, so if we have the same existential quantifier, the alternative one is, well, the hint, you just write it with an E to indicate that this is the alternative method. And we don't need to write the lines again. And the difference is here you say pick an x with, so the quantifiers in the propositions inside of the quantifier, so P of x and Q of x. And you can use P of x and Q of x anywhere in your proof after this line. Okay, so let's apply this to our example. So we're going to use, let's write the hint. Remember, this is the alternative elimination method on line 2. So our line number 4 is going to be pick with not P of y implies R of y. And now here, if you look what we have our three assumptions still, and we have derived not P of y implies R of y. But then let's look at the goal again. So we want to prove that Q of y holds. And let's see where we have Q of y here. Well, we have Q of y here in this for all quantifier. And right now we can't get rid of the for all quantifier because to get rid of the for all quantifier, we would have to have in the domain first, which is P of x. And nowhere in our proof we have P of x. And then you keep looking. Well, with this assumption you can't do anything because that just tells you that none R of y holds. You're assuming that R of y holds. Well, we already used the existential quantifier, so you see that we really need to get this P of x. So this is where you use proof by contradiction because there's nothing else we can do. And the way it goes is, so we want to prove P of x. Well, in this case, you want to prove P of y because you want the variables to be in terms of y. So here's where proof by contradiction comes in. You write down what you want to prove, which is going to be P of y, and you write down the hint, which is a quite long hint, and the hint is not intro on this line and something. Well, let me just get rid of what we have on the right so it doesn't take up space in our proof. Okay, so on this line and this line, followed by double elim. So as you can see, the hint for proof by contradiction is quite long. Okay, so we've written the hint, and what do we assume? Well, right here I don't have a lot of space, so I'm just gonna do one arrow like this. Okay, so I'm gonna continue everything on the right. So just imagine that these two lines, the p of y and the p of x, are here. Perfect. So we're gonna draw the flag like usual, and the actual flag. So let's just put it right there. And what we assume in proof by contradiction is the opposite of what we're trying to prove. So in proof by contradiction, we assume the opposite and then derive a contradiction and then say, well, since that gives the opposite gives us a contradiction, then the actual statement should be true. So the opposite of p of y would be not p of y. Okay, so now we have a new assumption, and let's see what we can do with this. Well, let's look at these two lines. Well, first of all, let me just write down the line here. The line number is 5. And let's see. We have not p of y, and on line 4, we have the implication not p of y implies r of y. And if you remember the rules for implication elimination, if we have the left-hand side of the elimination of the implication, in this case, if we have not p of y, well, then you can eliminate the implication and then get the right-hand side, which would be r of y. So let's just do that real quick. So implication elim on line, well, we don't need to write line, we just need to write the line numbers, which is going to be 5 and 4. And you will see that that gives us r of y, which is line 6 now. And whoa, what do you notice now? Well, let's see. We've derived a contradiction because, well, if we assume that not p of y is true, then we get that r of y is true. But before all of this, let's look at line 3, and we assume that not r of y was true. So if we have not r of y is true, and now we derive that r of y is true, then we obviously reached a contradiction, which is exactly what we were looking for. So that means that this assumption is wrong, and that tells us that p of y is actually correct. It holds. So that's perfect. So let's just write our hint. So what we're going to do is not elim on 6 and 3. And that actually gives us line 7, which is right here, p of y. So now we've derived p of y, and we're done because, well, we said that we wanted to prove q of y. Well, q of y, yes, and the only way we could get q of y is to get rid of this for all quantifier, and the only way to get rid of the for all quantifier was to get the p of x, and we have the p of y. So the only thing we need to do right now is just to write the hint, which is for all elim and this is on line 1 and 7. And now we're done because that gives us q of y. And this is a prime example of when you should use proof by contradiction, because from the assumptions we had, we could not continue the derivation. The only way we could continue the derivation was to prove that p of y was correct, and from the assumptions that we had, we could not get p of y. So we had to use proof by contradiction. And in this case, it was indeed the last resort. There was no other way of doing it. So I hope this video cleared up when you should use proof by contradiction, and well, it's always best to see an example in action. So again, just to recap, when you use proof by contradiction, so you want to prove some proposition P, what you do is you assume the negation of that proposition, so not P, you assume not P, and then you continue the derivation and try to get a contradiction between two things. You derive something and you have something before that, and you say, well, these contradict each other. So that must mean that not P is not correct. So if not P is not correct, that tells you instantly that P is correct. So that's the way we use proof by contradiction. Hope the video was helpful, and make sure you drop a like down below if you liked it. I would appreciate it very much, and it would help me a lot to grow my channel. Thank you for watching.